이번에는 두 번째 초청 강연은요, 스위스 내셔널 슈퍼컴퓨팅 센터의 디렉터이신 토마스 슐테스 소장님께서 슈퍼컴퓨팅 앤 서비스 오리엔티드 아키텍처라는 주제로요, 클라우드하고 웹 환경을 이용해서 스위스 슈퍼컴퓨팅 센터가 사용자 서비스를 개선한 사례에 대해서 소개해 주시겠습니다. 큰 박수로 맞아 주시기 바랍니다. 감사합니다.
Well, thank you very much for inviting me and giving me the opportunity to talk about our strategy, both on the HPC and cloud side. So Sunwook asked me to cover both our exascale strategy and our cloud HPC strategy. And after seeing the abstract of the talk Kathy Yellick gave yesterday, I decided to slightly change the way I will present this today. So I will narrow the focus on weather and climate rather than just giving you a general presentation over all the user program that we cover and the different areas of science. I hope it will become clear why I'm doing this, and I hope you will be able to follow the whole talk during the 50 minutes. Usually I run out of time towards the end of the talk, so I would like to start by acknowledging my collaborators on the climate side. I am myself not a climate scientist. I will explain in a moment why this is a topic that is of interest to supercomputing. But we have here some eminent scientists. Let me see if I get this. Yeah. Tim Palmer from Oxford and Björn Stevens from Max Planck Institute for Meteorology and Christoph Scher, a colleague at ETH, as well as Peter Bauer and Niels Wedi from ECMWF. Oliver Furrer, who used to work for Meteo Suisse and now has moved, unfortunately, has moved to Seattle, working for Valchem. And then a colleague, he's the only non-climatologist here in the list, Thorsten Höfler, a very strong computer scientist, well known in the HPC community. The topic, so I will show some data and discussion of exascale computing in climate, and this is summarized in this paper. The slides will be made available, so if you want to understand or you cannot follow all the details, you can always go back to this paper. Now, why are we looking at this problem to design our exascale roadmap? Well, there's a few reasons, but there's one that I'm not putting on slides because it may be politically not quite correct. But I firmly believe that supercomputing has been going a bit in the wrong direction by focusing too much on top 500 and the high-performance LIMPAC benchmark. And we've come to the point where we design machines to rank high on that list, and then these machines are not very useful in science. And I personally, I'm a scientist, I'm very concerned about this, a computational scientist. And so we decided to rather than use that benchmark or pretend that we take science seriously but then end up with the top 500 machine, I decided that we should have a science goal, a motivation coming out of science, take one area and co-design a system around that area. And we are picking weather and climate because this is probably the most general use case that we can come up with that covers both scalable computing, big data, remote sensing, everything that you want, all in one use case around one science goal. And so this is one reason why we pick this. The other one is because at CSCS we have considerable experience with the topic from an infrastructure point of view, because we are not just running a large supercomputer for which the center is known, Pitt Stein, because it is highly ranked in top 500, but we are also running the operational system for weather forecasting for Meteo Swiss. So we've designed and we now operate this system, or we've been operating a system for Meteo Swiss for quite a long time. And one of the systems that we have, it's actually already 4 or 5 years ago that we have introduced a GPU-based supercomputing to run an operational weather forecasting model. And this was before the deep learning revolution. So today, ironically, everybody thinks that GPUs are used for AI and deep learning. It turns out you can run a full-fledged weather model as we did. And so some people wonder, why did we do this? Well, the Meteo Swiss in actually 2013 presented us, so 6 years ago, presented us with a challenge. So they wanted to upgrade their model, meaning they wanted to increase the resolution from 2 to 1 kilometer. And this is, the picture there is a bit misleading. So it's 1 kilometer resolution in the horizontal, so you have a factor 2 by 2 means a factor 4, and then you have the CFL condition, the time step that you have to reduce. And that gives you roughly a factor 10 more in performance. Then they wanted to introduce an ensemble simulation at 2 kilometer resolution, and that was another increase of 24 in performance that was necessary. And finally, they wanted to improve their data, or had to improve their data assimilation. So overall, we're talking about a factor 40 in needed performance improvement at a fixed budget and over a time scale of 3 years. So we had just bought the system in 2012 for them that was running the 2 kilometer model, and they wanted the new system 3 years later that had 40 times the performance, but was not allowed to cost more. And in operations was not allowed to cost more either, so not more power. And so how do you solve this problem? Well, it turns out we had, on the climate side, been investing already in a rather large software project. And so Meteo Swiss is running this model called from the Consortium for Multi-Scale Modeling. So this is a limited area model, which I believe is also run in Korea. I know that it's on the map of the Cosmo Consortium. So it's a limited area model that's developed by several weather services and used in academia also for climate research. And what we have done is, one of the first things when I came to CSCS, we've been looking at this code, which is a monolithic Fortran code. You can say just a lot of lines of Fortran code. A typical climate model consists of the part that solves the dynamics and the part that solves the physics or chemistry. And we've been refactoring or rewriting some of the software. So very important, the new implementation on the dynamics, which consumes most of the time in computing, is a fully rewritten code with a modern modular or composable software structure. And the key point here is we have a stencil library in there that deals with the grid, and that is designed in such a way that it would support different architectures in the backends. And so we are supporting x86. We are with OpenMP. We are supporting CUDA for GPUs. We're supporting with OpenMP again Xeon Phi and the more modern Xeon processors with longer vector instructions. And then the new AMD GPUs, and we're looking at ARM currently. And given this situation with the software, we were then able to design a system that would basically maximize the performance, minimizing cost, and improving throughput. So that really allowed us to implement this on GPUs. And then one of the lessons learned, and this is also to be taken as we look into the future for exascale, is we can now compare the code running on different architectures, the new code, new implementation versus the old one, and we can now discuss how we beat this factor of 40. And it turns out that the investment in rewriting software, that alone led to a factor 2 improvement. And this is a professionally written code. In many cases, when you start from a non-professionally written code, there's a factor 100 there that you can easily reach. Then, once you've cleaned up the software, you can also do mathematical improvements, change in architecture, and then we had, of course, Moore's law at the time still helping. This is middle of the decade, and we had to increase the number of sockets. But because the GPU is power efficient, that increase in the number of sockets would in the end not increase the power consumption of the machine or the cost, and it would, in fact, the machine is cheaper to operate, so the power cost went down. But the main message we take from this is there is no single bullet. So if you want to go to higher performance, you have to work on all sides. Of course, there is hardware, there is architecture, but there is software and there is mathematics. And you have to work on all things as you move forward. Now, experience is one motivation. The other motivation is that there is really a problem that we need to solve. And this is a problem not just interesting to a few scientists, but this is concerns everybody in society around the whole globe. And I just realized that I'm going to be worried about this tomorrow when I try to fly back to Europe. I've overheard some conversation this morning at breakfast that it's not recommended that I fly tomorrow, but I will find out. So this is about prediction of storms and weather prediction, where today it is very remarkable what we have reached, particularly our collaborators at ECMWF, in terms of the quality of prediction a week or two ahead of time. And in the US, we are using this very much, these capabilities when it comes to predicting hurricanes. But the challenge is that in the models today, there are still, because the resolution is not good enough, some parts that are missing. And the one that is of most concern to climate and scientists and meteorologists is how convective clouds are described. These are these stratocumulus, or storms being thunderstorms, for example. You can imagine if your climate model has a resolution of 10 kilometers, that you will not resolve clouds like this, or not even individual thunderstorms. But they are a big part of the energy balance in the tropics, and so you somehow have to describe these things in a better way. And the question is, can we reach a resolution that resolves these type of clouds? And it turns out that something surprising is happening, and this is an opportunity that we have in the coming years. So when you look at these type of situation, and you try to solve the full atmospheric problem, you come very quickly to the realization that there is no hope of solving the full problem. But so that's what we mean with structural convergence. So to have a model that really predicts where which cloud is going to be, or to the full distribution of clouds, is probably hopeless. But it turns out when you look at the bulk properties, so the first moment of the distribution, there is actually some hope. And the hope is going to we can deal with, I will claim here, with exascale computers. So this is this if you look at the cloud coverage, the relative frequency for different cloud areas, looking as a function of the resolution of the model. So this is the horizontal resolution. You can see that actually the full distribution does not converge as we reach 1 kilometer, 500 meters. Today's models are around 10 kilometers, the global models, okay? And so we would probably have to go down to 10 meters, which is, for anybody who knows computing, is very far out from what we can do today. But surprisingly, the bulk convergence, so looking at the average coverage, the area, seems to converge around 1 or 2 kilometer scale. And so this means now that we have to push computing to enable climate models to reach this 1 kilometer scale, and this is what I'm going to try to estimate if this is possible. Now, what we are showing here is the development of ECMWFs. This is the European Center for Mid-Range Weather Forecast, evolution of the performance of their model over the decades they exist. So they were founded in the late 70s, and they started to track the data in the 80s, apparently. So this is the resolution of the model, the complexity of the model measured in degrees of freedom, so number of columns times number of levels times number of prognostic variables to the three quarters, a power of 3/4 to account for the time step. And you see an exponential increase that more or less is a bit slower than Moore's law. So Moore's law used to double the performance every 18 months, and here we double every 24 months only. So the climate community has been moving slower than Moore's law, and certainly slower than the top 500 HPL benchmark. But still enjoyed an exponential increase in performance. And when you look, we are somewhere around here. That's what I said, around 9 or 10 kilometers. And when you look at what their goal is to reach kilometer performance by the mid-2030s. And the argument I'm making to this community is, we will no longer have Moore's law as we move forward. So we will have to deal with architectures, we have to do something. Just waiting is not going to help us. But when you now say, we exascale, meaning in the early 20s want to reach a kilometer, that means we're basically pulling in this goal. So we not only just don't have Moore's law, but we have to pull in the goal by 10 years. So is this not a crazy idea? Well, it turns out, before we say it's crazy based on such a discussion, it turns out, let's look at where we are. And to say where we are with regard to the goal, we have to clearly define the goal. And so we sat together with our colleagues and define what we really mean in performance. The details probably are of no interest to you, but I just add them. So one is this horizontal resolution of a kilometer, 180 levels in the vertical. The time step has to be less than a minute. In fact, it should be around half a minute to describe the physics properly. And then all these other things like coupled model, non-hydrostatic atmosphere, and the precision we allow to go to mixed precision or lower precisions. And it turns out this is one of the more interesting problems to look at from a numerical point of view these days. And we want to have a throughput of the model of 1 simulated year per wall clock day. Then, once you have the goal, you can say, where are we with regard to this goal on today's machines? And what we've done here is we've used our supercomputer PIT-Stein that has both GPU capability and CPU capability. And we've been testing the Cosmo model that I discussed before, that we have in operation for Meteo Suisse, and IFS, which is commonly known as the European model in this mid-range weather forecasting. And so I'm not going to go into further detail, just present the results. So this is running both models at full scale, around 5,000 nodes, and measuring the performance. And now you can go through each of the items that I presented before and give a penalty for the shortfall. So for example, the vertical resolution in both models is currently run at 60 levels, needs to be run at 180, so we have a factor 3 penalty, or the throughput is too slow, so we have a factor 23 or a factor 10. Then you multiply all these numbers and you find that Cosmo is roughly, if we run it today or on a 2016 Pitstein technology, is roughly a factor 100 away from the goal that we would like to reach in 2022. And IFS is around the factor 250 away. Now, you can say, well, that's a lot, but we can try to analyze, what are the reasons for the performance shortfall, and can they be overcome in this time frame until the early 2020s. In the case of Cosmo, since we have been working on this for close to 10 years now, we have a lot of information about how to what is the performance model, and how is this code performing. And one of the things, and this has also been published in this reference here, is how do you assess whether a code is, how far is it from peak performance? Turns out looking at fraction of peak in terms of floating point performance is not very useful. I know it's because this is a result in the end. It doesn't really tell you much about what you need to do to fix it. Okay? The mathematicians say, well, you need to increase the arithmetic density, but it turns out this is not very useful in climate models. There's a debate over that. Because you're not just looking at the fluid problem, you're also looking at coupling to physics, and those are low-order couplings, and so increasing the density and increasing the order of integration while you're forced to use a low order of integration is not very useful. So what we are looking here is at the what is called we called memory use efficiency, which is because we know today on most applications, the sensitive part is not how we use the floating point units, but is how we use the memory. And this efficiency consists of what we call I/O efficiency, and this is I/O to main memory, and the bandwidth efficiency. And the numbers come together by looking for the I/O efficiency. Given our method that we try to implement, this finite difference method, what are the necessary memory transfers, the minimum necessary to come to a solution, and this can be estimated with graph theoretic methods, and then you can measure the actual number of transfers. And then when we do this for Cosmo, we find that we are about 90% efficiency. So one would be optimal implementation. So the current implementation is not too far off. It still can be improved, but not by a factor 2 or by a factor 4. The more interesting part is now how do we use the memory bandwidth on the system, and this is now not something that's in the control of the application developers, but it's something that the vendor and the people who write the drivers for the memory look at or control. And here we're looking at the ratio of achieved bandwidth compared to maximum achievable. What we are taking here is the stream bandwidth. If we take the the peak bandwidth, the numbers look worse. Namely, here we achieve 0.6, but if we take peak bandwidth, it would be 0.5. So we're a factor 2 off from, where we think we are when we buy expensive high bandwidth memory. So we've done an analysis, and I think it all has to do with something that's very well known, namely that the DDR memory protocol is not good when it comes to non-stride WAN access to data. And the detailed study shows that this is in fact the case. So one of the things that we take away from this when we move now into the future is that we have to pay attention to the memory bandwidth and how it is used on these systems. Okay, so rather than go into each and every detail, I'm just now summarizing how in Cosmo we might overcome this factor 100. One thing we know, that Cosmo is this lat-long grid, so it's a very inefficient grid to solve the problem on a globe. And so by rewriting the software and using a homogeneous grid at 1 kilometer, like icosahedral or octahedral grid, we could get out, just by the rewrite and support of different grids, we can get out a factor 4. And this is because there's a factor 2 in having fewer grid points, and then a factor 2 because they are further apart, and therefore the time step can be slightly larger. Then we have a factor 2 from this memory efficiency problem I just discussed. We can study the scaling, the strong scaling properties, and we find there's another factor 3 of strong scaling potential that we have in there. And so we can assume if the GPUs become more potent and more threads per socket, and assuming that we also have the bandwidth under control, then we should be able to scale another factor 3 there. If you multiply this, you get to 24, and so we still have a shortfall of a factor 4 that needs to be overcome, either through better time integration schemes or further improvements to the processor. But it is doable. Something that, with very thorough investments in both hardware and software and refactoring of application software can be overcome. And so this is what we call our exascale challenge. The challenge we would like to meet without increasing bit time. So we could overcome like the strong scaling by just making a machine that is 3 or 4 times bigger. But we are not planning to do this, and the reason is because the 1 simulated year per day is just the first step that we want to achieve early next decade. We need to go further. The climate scientists really would like to have a throughput of 5 simulated years per day. And how will this continue in the 2020s when we have no more Moore's law helping us? And particularly because I said in terms of implementation, we're already near optimal. Well, near optimal is on today's architecture, so on a control flow centric architecture, and we have all these difficulties about, we are stuck with the performance of memory. And but you could argue that you can change the number of necessary transfers if you would switch to a data flow architecture where you say, okay, you read in from memory what you can, but because you can reconfigure the processor and optimize the data flow, which is not the case today, you can reuse the data much, much better, and therefore reduce the number of necessary transfers, and then you can also reduce the number of actual transfers. And so then this whole equation we'll have to look at differently. So that is one option, to switch to something some people call coarse-grained reconfigurable array or near-memory computing also. Now there is a different challenge, and this is why I'm so sensitive about the footprint of the simulation, is that we don't need just one trajectory. We need to simulate, say, of the order of 10 or 50 trajectories. And here, what we have to do is either further reduce the footprint, which probably is not possible, or we have to go to a different scale of simulations. Something that the cloud community knows, rather than have a supercomputer like BitStein that uses 4 or 5 megawatts, we build one that uses 200 megawatts, and then we get our factor 10 or 50 or so out. And you may think that this is crazy. Well, we have in Europe a collaboration. This is a consortium of 9 countries putting money together with the European Commission to build a new system that will be deployed in Finland in a data center north of the polar circle. This is an ongoing project, and it's not going to be a hyperscale machine. But my main interest in this, apart from collaborating with other countries, is the data center they have up there. They have a repurposed paper mill, that is now a computer center, and that has a number of characteristics: very reliable power, close to very reliable and powerful networks, and most importantly has a hydroelectric energy capacity of up to 200 megawatts. So you can see this is where we are going to build those systems in the mid to late 20s. I'm convinced that that's what we will be doing. Now, of course, somebody will have to worry about how do you finance these systems? And there I'm saying, let's worry about that later, because I'm pretty convinced that the financing will be there once we have proven the capability that we can do with these supercomputers. And you just look at this, for example, report from the UN that is looking at the damage, both in terms of fatalities and cost over the last economic losses over the last 20 years due to natural disasters, or this assessment of the World Economic Forum that is putting climate extremes, weather extremes, really at the top of both the likelihood of things happening and the damage they cause. So you have, for example, nuclear weapons here, which would cause enormous damage. These are comparable damage, but of course the likelihood, as long as politics stays under control, those events being small. So these weather extremes, weather disasters is something the global society has to deal with, and it is something that we have to be able to at least simulate, analyze, and understand, so we can be prepared to deal with these things. And so in Europe we have, this is the map of ECMWF. This is this organization with 34 member states, including non-European member states like Morocco, Israel, and Turkey. And within this organization, there is a number of organizations, including ETH, which I belong to, but also Jülich and Max Planck Institute, etc., Max Planck Gesellschaft, from these blue countries that come together and created a consortium to look at what is necessary to model these extreme events in the future. The consortium is called Extreme Earth, and they are doing the same in big compared to what I've been discussing now in the small. namely the co-design of both science, the technology, and the societal needs in this area of extreme events. And in the technology, we are really looking at three things. Okay, we have to, on one side, look at the computing problem that I've just discussed, and I think we have under control. We are looking at data problem, and I think the data problem is again under control because otherwise ECMWF would not be making the forecast, but you have to consider that this is probably today it is fancy to talk about big data, and all scientists brag about the type of big data problem they have. Turns out that this community had a big data problem since about 40 years, since they exist. They have remote sensing, they have data assimilation, they have the large simulations, and then they have the processing of data after the simulation. And we take this for granted, like when we look at the weather forecast for tomorrow again with this typhoon approaching. So that's the technology that's going on behind. And what we need is a combination now of these large data problems, large computing problems, and the entire workflow. And that's really going to be the probably even bigger challenge than the exascale challenge I've been discussing. Namely, we need to create a cloud, they call it Extreme Earth Science Cloud. And what I would like to address now in the remainder of the time is from a technology point of view, not the social point of view behind this, how we can address this. Because this is a problem that supercomputing in more general has to address. And what I call the convergence of HPC and cloud. So not running a cloud and a supercomputer, but I'm really talking about running a cloud on a supercomputer. And so it's the use case of weather and climate is very prominent and probably going to be the driver, but more generally, the scientists we work with are calling for this. And this is a well-known colleague in machine learning, not giving the name, basically made a comment a few years ago and said, we develop algorithms, we're not interested to deal with C++ or MPI. And it turns out sometimes professors don't follow what their students actually do. The students are not of the same opinion because they have to implement his ideas. But still, what he's basically saying here is reflected by the broader community of scientists, and you've heard it yesterday in Kathy's talk, I'm sure, and you mentioned it again. What we need is a convenient environment to work with, and for example, today, the environment of choice for many is these Jupyter notebooks that not only allow you to develop programs, also allow you to deploy calculations and to document the workflow. So it's something that when you work with students and interact is really extremely useful to have. And of course, what you want is to run this on a supercomputer. Now, we have at CSCS a couple of years ago started to introduce a service, or actually a year ago, and we've not been advertising the service very aggressively, but you can see that the users pick this up. This is really using Jupyter Notebook on PitStein. We are also using it to teach classes, like this is a library. Arbor is a library, domain-specific library for neuroscience. Neuroscience is a community that really doesn't want to have anything to do with interacting with a supercomputer, but then they have problems that do need a supercomputer. And but that's one thing, to have a notebook and some interactive service running on the system. The more challenging question is, how do you deploy the software or the computation on this large system. So when you run Jupyter Notebook on your or IPython on your laptop, the deployment is something very easy. You just execute on your laptop. But if you execute a 1,000 node job, you know, how is this going to happen in practice? Now in the cloud, this happens usually with virtualization, where you can actually run off your application, you know, everything together with the operating system under which it has been developed. And, but this is not something we want to do in HPC, and of course the solution that has been developing over the years is this, this idea of running containers, where you can run the application on the bare metal system, provided you have the proper engine to do this. And it turns out the Linux environment with C groups has the context to do this, the technology. Of course, when you try to do this now in practice, you're faced with a challenge. We have two types of classes of runtime systems or container engines. We have Docker and the ones developed in the cloud, which have the advantage that they can run a full software stack for AI or cloud. And then we have a number of runtimes that have been developed mostly by DOE labs. This one is by NERSC, where Kathy may have been talking about yesterday, that run on supercomputers. And our challenge with running cloud on a supercomputer is, of course, we want to do both. And so we have to find a solution. And we've been working on this now for 3 or 4 years. There's a number of desired features that you have. Namely, you want to be able to achieve native performance when you deploy the software with a container. You want to have a suitable parallel file system. This is the weakness of the cloud solutions. And this is what Charlie Cloud or Shifter or Singularity are trying to address. You want to have all the necessary security measures on the multi-tenant system, compatibility with workload managers, and easy integration of vendor support. So this looks like a rather complex list to bring these two things together. But it turns out, and this is one that I've added, I'm not interested in a new interface. I want Docker, because this is what most of the users are familiar with. So I don't want some new interface. I just want what people are used to use. But it turns out that the team around Lukas Benedicic at CSCS has found a remarkably simple solution. And that is, if you're not trying to write everything from scratch, but you're adhering with some of these standards of the Open Container Initiative, it turns out that all you have to do is put together a package, we call this Saurus, that has a command line interface through which the user can configure the containers. You can import existing Docker containers, and all the package has to do is provide one of these OCI bundles, so they are defined in the by a standard that provides a root file system to give access to a parallel file system, and a configuration file that then can interact with the runtime. We are not writing our own runtime, we're just using an OCI compliant runtime, in this case rsync, and the key is these OCI hooks, which are the opportunity where the facility like CSCS or the vendor, in our case Cray, can provide details of the configuration to the runtime, how to deal, for example, with MPI or GPUs. And with this separation of concern, the Docker engine becomes very lightweight. And as the results show, I'm just showing a few examples, of, for example, GROMACS, which is a molecular dynamics code, comparing the container in red and the native performance if we run optimized GROMACS on the system. And you can see they are almost indistinguishable. The same is true for containers we download from the web. This is TensorFlow. Again, executing in container or on bare metal natively is almost the same performance. And Cosmo, the climate application I've been talking before, running on, and this is just showing the results up to 2,000, but it does scale up to 4,000, 5,000 nodes. Again, comparing Cosmo running natively, fully optimized, and running within a container using the Saurus environment. And there is no noticeable performance difference. So we do have probably solved one of the most important problems for these cloud-like operations is how to deploy software at scale and seamlessly on a supercomputer. Now, the last item I want to cover is this question of how the infrastructure is accessed. Traditional supercomputer is like a very large workstation. So you have a user interacting with a login, probably through SSH and with a large computer in the background. And he's doing this or she's doing this on behalf of a research community. It turns out we had several projects in the last 5 years, like the high-energy physicists doing their data analysis for the LHC in Switzerland. And this is a material science project, and this is the human brain project. They would like to have a web-accessible interface to the supercomputer. And with quite a bit of effort, we've managed to do this. So, for example, CHIP, the Swiss grid for high-energy physics, today is running on Pitstein, on the supercomputer. It's not running on the distributed grid, and that's because it's cheaper to do it this way. So we've moved the middleware, and the users of the grid use the grid, but they don't see that they are actually using a supercomputer in the background. The problem with this approach today is it doesn't scale. There's a lot of work we have to invest for each and every platform. If you have a very large infrastructure, you want this to be automated. And the solution, of course, is known. It's just hard work to do it and non-trivial. Namely, you have to separate the actual HPC infrastructure from the platform through developing REST APIs to access the infrastructure. And so this is work in progress. It's a new product we call Firecrest, which the idea is really to make the supercomputing center web accessible and programmable. And I'm convinced, again, this is possible. And then if we've achieved this, and we have a number of demonstrations with these platforms that we can achieve this, then comes the next problem, and this is the final problem, is availability. Supercomputers are efficient, secure, everything, because they are very well-maintained infrastructures. There is usually the legacy in software is not older than a few years. If there is a problem, then there is a fix for the problem, a security problem relatively quickly, but it also means that we have to maintain the machine and take it down every few months. Now, if you are a user of the machine, you get notified, you understand the problem. If you're a user of a service that runs on the machine and you have no idea about the machine, you are not happy if the service is down. Okay, so the question now is, how, using HPC systems, you can achieve 99 or higher than 99% availability. And the answer is through federation. So that you basically operate the service in a number of supercomputing sites. That means you have to replicate some of the data, and you have to think about this and be very strategic at the platform level. But we do have another project in Europe where we, CSCS, collaborating with Gineca, Jülich, CEA in France, and Barcelona Supercomputing Center, are testing the deployment of this infrastructure in a federated way, and then we will see if we achieve high availability. The challenge here, of course, and this is why you have to test this, is each and every country cannot afford to have 3 or 4 sites of this scale. Together, they can. But then you have to overcome the political barriers and the different cultures in how different countries run their supercomputing infrastructure, and that's what we are working on. So that pretty much completes, and as promised, I've covered both sides, and if you have questions, I thank you for your attention. I need to acknowledge the people who worked on the cloud side, and if you have questions, I'm available still also today after this talk or after the session. Thank you.
Yeah.